Okay, so we are getting into chapter 3.11, and this is on linearization. And so, got my pen. Okay, so for example, if we have some graph, and let's say that this is f of x. So recall, if we took some point, so let's say some value of x equals a. Let me pull this up. We were able to, right, find the equation of the tangent line. X equals a. And so remember how we did that? We needed a point and we needed a slope. And so we found our point, right? We have a point. Well, we said our x value is a, and so our y value is going to be f of a. And our slope, well, we talked about taking the slope, we found the derivative, right, of our function. And if we wanted the slope at a particular point, then we plugged in that x value of our point. I can't find black. It's okay. And so we would look at f prime of a. Okay, so when we were finding our equation of the tangent line, I typically used the slope-intercept form, y equals mx plus b. But some of you and the book a lot of times used your point slope form. So let's just kind of write out the point slope form here. And so remember, this was y minus your y value of your point, which in our case is f of a, is equal to your slope. Our slope in our case, right, is f prime of a, all times x minus the a value of our point, or x value of our point, which in this case was a. And so we have our point slope formula. And so let's look at this and let's just get y by itself. So if we got y by itself, y is equal to, we can add f of a on both sides of our equation. So y is equal to f of a plus the derivative, or slope at a, f prime of a, all times x minus a. And so this was the equation of our tangent line at some x value equals a, if it was differentiable there. So what we're going to be doing is we might have some complicated function and we might want to figure out what some value is at that function, which is near. But if we can notice that if we choose, going back up to my function, if we choose some point that is really, really close to this function, we could actually estimate what it is by going back in and plugging it into our tangent line. And so that's what we're going to be doing when we're doing this linearization. So we're going to be using our function, we're going to be finding the equation of a tangent line at a point, choosing a point of a value that's easy for us to find, and then estimating the value that we wanted by using the equation of the tangent line. And so y here, or f of x, is another way we write y. This is also L of x. So linearization, this is approximately equal to f of x, our y value here, which is equal to our f of a plus f prime of a, all times x minus a. So this is our linear approximation. So if you get to a different page without screwing everything up. Okay, so let's look at an example of using this. And so actually I was going to do a natural log, but let's go with a simpler one first. Let's do a square root. And so, for example, let's find the linear approximation. I probably should have typed this out. It could have been faster. Next time. So find the linear approximation of the square root of 9.06. Okay, so a couple things that we want to do. We want to figure out what our function is that we're going to use. And so looking at this, I can tell f of x, let's choose this to be the square root of x. And a number that's close to 9.06 that we know how to take the square root of would be 9. And so here we're going to choose a to equal 9. And so by that formula, we knew that the linear approximation formula that we're going to use was equal to f of a plus the derivative of prime of a all times x minus a. And so it's pretty easy to take the derivative of the square root of x. And so if we took the derivative of the square root of x, so bring down our power, subtract 1 from our power. So this would give us 1/2. Subtract 1 from our power is now -1/2. That brought us down to the denominator. So I'm going to kind of just skip the step and rewrite it as 1/2 square roots of x. So we need to figure out what f of a is and f prime of a is. Oops. So f of a, you know that this is equal to the square root. Well, a is 9. So this is equal to 3. So I know here that f of a is 3. So I'm going to place it into this equation. So I have 3 plus, so f prime of a. So let's figure out what f prime of a is. And so f prime of a, so f prime of 9, plug that into our derivative equation that we found down here. So that's 1/2 times the square root of 9, which is equal to 1/2 times 3, which is 6. So f prime of a, we just saw was 1/6. So let's plug it in here. So plus 1/6 all times x minus a, but a was, in our case, 9. So now we can figure out approximately what the square root of 9.06 is by plugging it into this equation. So we have 3 plus 1/6 all times x, which is 9.06 minus 9. So cleaning that up, we have 3 plus 1/6. Well, 9.06 minus 9 is 0.06. And 1/6 times 0.06. Well, 6 goes in there evenly. So it goes in 0.01 time. So this is equal to 3.01. And because we are approximating, I'm going to actually change the equal to approximation instead of the equal sign. So if you took out your calculator and you plugged in the square root of 9.06, it should be approximately 3.01. So let's just plug that in. And where's the stupid square root button? I don't even see it. I use this calculator very often. So 9.06, I can raise it to the 0.5 power. Same thing as 1/2. So I get 3.099833, and we said it was 3.01. So our estimation is really close. So they might ask you on your homework, what was the estimation error? And so you would look at your answer here and the correct answer and subtract it. So any questions on that? Okay, so let's do another example. So use linear approximation to find the natural log of 0.9. So first thing you want to do is find a function that's going to represent the natural log. And then you're going to try to find some value a. Such that you know what f of a is. I'm going to find f of a and the derivative at a. Okay, so looking at this, I can tell that we should let f of x be the natural log of x. So recall, if you had y equals ln of x, by definition, what this is saying is, what is the exponent you can raise e to get back x? And we need to choose a number that's close to 0.9. And so we should choose a to equal 0, not 0, 1. And the reason why that is if we had y is equal to the natural log of 1, well, e to the y is 1. What number can we raise this 2 to get 1? This is equal to 0. Okay. I don't know if that was helpful or not. I'm going to erase it. Okay, so we want to choose a to equal 1. We know what the natural log of 1 is by what I just showed you. And so now we need to look at the derivative. And so the derivative of the natural log of x wasn't bad, right? This was equal to 1 over what you were taking the natural log of, which was x, times the derivative of what you were taking the natural log of, but the derivative of x was just 1. And so now if we plug in our a value into the original, so f of 1 equals the natural log of 1, which we just said was 0. And if we plug in 1 into the derivative, wherever we saw x, we get back 1. So the linearization of our number is equal to f of a, so in our case, f of 1 plus f prime of 1, our slope at that value, all times x minus a, which is 1. So f of 1 was 0 plus 1 times x minus 1. So x minus 1 is the equation we're going to use for our linearization. And so if we want to look now at, what was it? Ln of 0.9. This is approximately equal to L of 0.9, which is equal to 0.9 minus 1. Which is equal to 0.1. So the natural log of 0.9 is approximately 0.1. So if I pull this up again, sorry, and I would go down to natural log, actually need to clear it. Okay, so this calculator is a little different. So you have to actually put in the number first. So if I put in 0.9, what I'm taking the natural log of, I get, it says negative 0.1. Hold on, let me calculate right here. Oops. And that's right? Negative 0.1. 0.9 minus 0.1, the larger number is negative. Okay, so if we wanted to look at what the error was. Oops. I don't know how to get out there. So like I said, it might say use your calculator to see what your error is. And so if I look at f of 0.9, I get that negative 0.1053. And so I'm off by 5 thousandths, which is not bad at all. And so this approximation is a good way to approximate something that you know how to find and is close to what you're trying to find. So what if it said use linear approximation to find sine of 18 pi over 17? So use linear approximation. So 18 pi. Oops. Darn it. Okay, so looking at it, you should be able to tell what you're going to let your function be. And so we could choose f of x to equal sine of x. We know how to work with sine of x. We know what the derivative of sine of x is. So sine of x, the derivative was positive cosine x. We want to look at some value that we know how to do that is close to 18 pi 17ths. So I know how to figure out what sine of pi is. 18 pi over 18 is close to pi. 18 pi over 17. So let's choose x to equal pi. And so we could figure out what f of pi is and what f prime of pi is. So sine of pi. So sine, remember, is the y value on the unit circle. Pi is at the negative x-axis, and sine is 0 then. And cosine of pi, this would be -1. So the linearization we're going to use is f of pi, which is 0, plus f prime of pi, which we found to be -1, all times x minus a, which was pi. So this is equal to negative x plus pi. We distribute our -1. So sine of 17 pi over 18. This is approximately equal to L of 17 pi over 18.
Is it 18 pi over 17 or is it 17 pi over 18?
It's 18 pi over 17. Thank you. Yeah. Let's just get rid of that. Thank you. So sine of 18 pi over 17. Is equal to, or it's approximately equal to L of 18 pi over 17, which is equal to negative 18 pi over 17 plus pi. But if we want to get a common denominator, we can rewrite pi as 17 pi over 17. So this is going to equal negative pi over 17. Which if we plug into the calculator, that would give, oops. Approximately negative 0.845. Negative 0.185. So if you put sine of 18 pi over 17, make sure that it, first of all, that it's in radians and not degrees in the calculator. And so sine of 18 pi divided by 17. So that gives me approximately negative 0.1837. And I had 1/8, and I rounded that 4 up to a 5. So again, we're really close. We're out to the thousandths position on how close we are by using the equation of the tangent line close to a value that we already know. I'm just trying to look at which one to do. So one more example. So if it said estimate e raised to 0.01. So same kind of reasoning. We can look at a function e to the x. We know what e to the 0 is, which is 1. And so we can look at the equation of the tangent line of e to the x to figure out what, or estimate what e to the 0.01 is. So let's choose f of x to equal e to the x. Well, if you remember that derivative, then it's probably the easiest one ever. It's just itself, e to the x. If we choose x equals, well, number close to 0.01 is 0. And so derivative of 0 and f of 0, same thing. Which is 1. And so we know that L of x is equal to f of 0, which is 1, plus the derivative at 0, which is 1, times x minus a, which is 0. I'm going to rewrite that. I said x equals 0, but we were looking at a equals 0. So this, in this case, is just equal to 1 plus x. So e to the 0.01. This is approximately equal to L of the 0.01, which is equal to 1 plus 0.01, which is 1.01. And so if you look at your calculator and do that, e to the 0.01 is 1.010050167. So again, we're really, really close there. Tens, hundreds, thousands. So 100 thousandths position. So the estimate is really close. Okay, so any questions on that? So let's, let me